is y is equal to x cubed, right? And as a result, you're going to have, or you're going to expect that your function is going to start from quadrant 3, right? And then you're going to have somewhere, something on quadrant 1, right? Because it's positive leading coefficient and it's an odd degree. Okay, so we have that written down. Now, how do you draw your graph, right? So when you're drawing your graph, you're going to have -3 and 2, right? Again, we mentioned because it's starting at quadrant 3, that means you're supposed to have your function starting from the bottom, right? So you're starting here and drawing up. So because at -3, you see that it's 3, right? It's an odd multiplicity, however, it's greater than 1. That means you're going to have what you call an inflection point. So an inflection point is also crossing, right? But it's a little bit flatter because you have a change in, there we go. Okay, there we go. So this is flatter as opposed to just crossing because you have a change from concave to convex. Basically, that's what it is. So it's like this right here. So you have a change in your concave to convex, and then this is a little bit flatter, right? So that's what happens at -3. But if you have, let's say, at 2, right? If you're looking at x minus 2 and this is 2, you're just going to bounce, right? And how do you know it's not going this way, right? Going down? Well, if your function is odd, that means you're going to finish at quadrant 1. So that means it has to be on top of your x-axis, right? Or above your x-axis. So you're going to bounce here. Okay, so see that bounce? So it only touches your is equal to 2 and it doesn't cross that because it's an even multiplicity. Okay, so for even multiplicity, right? For example, if it's greater than 2, what happens to your bounce is it just becomes flatter, right? The greater the number, it just becomes flatter. So for example, this is when multiplicity is 2, right? Versus when multiplicity is 4, right? It just becomes flatter. So this is 4. So when you're graphing, it's just really your intuition that you need to make it flatter. Okay. So I think I've covered everything that you need to know for polynomial functions. And yeah, hopefully this is making sense so far. If you do have any questions, please let me know. Okay, cool. So let's move on to question C. Okay, we can see that this is a rational function, right? So if it's a rational function, that means you're going to have a numerator and a denominator, right? So respectively, you have x minus 1. So if it's a rational function, you need to determine whether it has asymptotes, right? Because we know that rational functions have asymptotes. So we can start with vertical asymptote. So for vertical asymptote, you can really assess that in your denominator. So the whole point of a vertical asymptote is your function does not exist there because you have a break there, right? So at x minus 1, which is x is equal to 1, that's your vertical asymptote. Okay, we do have more space at the bottom. So vertical asymptote is x is equal to 1, right? And how do I know it's x is equal to 1? Well, if it's in your denominator, that's going to be your vertical asymptote. And the reason for that is because if you have, let's say, -2 over infinity, right? How do I know this is approaching infinity? Because your vertical asymptote, you don't have your function existing, right? So x is equal to 1, right? And what about your horizontal asymptote? So horizontal asymptote, you're now looking at y, right? But for y, right, you first have to figure out the degree of your numerator versus the degree of your denominator. So horizontal asymptote, again, you have to assess whether your degree of your numerator is less than, equal, or greater than the degree of your denominator. Okay, so here's the following conditions, right, for horizontal asymptotes. If the degree of your, so DEG means degree, if the degree of your numerator is less than the degree of your denominator, so DEN is denominator, that means your horizontal asymptote is 0. Does that make sense? So you don't really have, so in this case, your horizontal asymptote would be 0, right? But, so there's a difference between 0 versus none, by the way. If you say horizontal asymptote is none, that's completely wrong. So you need to make sure if the degree of your numerator is less than the degree of your denominator, it's 0 and not none. Now, moving on to the degree of your numerator, which is greater than the degree of your denominator, and it's only by 1. Okay, so why are we emphasizing that it's only by 1? Well, if it's by 1, that means you're going to assess whether you have a slant asymptote as opposed to horizontal asymptote. So you call this slant or oblique, depending on, again, your teacher, which they prefer, he or she prefers rather. So it's slant or oblique asymptote. So that's what you look for. But in this case, degree of the numerator greater than the degree of your denominator, horizontal asymptote is none. Even though if it's greater than 1, and even though it's just by 1, if your degree of your numerator is greater than the degree of your denominator, your horizontal asymptote is none, not 0. And if it's equal, right? So degree of your numerator is equal to the degree of your denominator, which we're going to look at for the next question, which we can see here at the bottom. If you guys can see this, you can see that the degree of your numerator is 1, the degree of your denominator is 1, and they're equal to one another. You need to look at your end behavior. So in that case, you would have to divide your numerator and your denominator with the highest power of x, right? I'm gonna go over that in a bit, so this is gonna all make sense afterwards. So equal to numerator and denominator, therefore there should be a horizontal asymptote. And the horizontal asymptote is basically the ratio of A and C, right? So A is 5, 2 is your C, because it's AX minus B plus CX plus D, right? That's one of your rational functions. Okay, so we can actually say that this is y is equal to 0, and we can move on. So now we have vertical asymptote, horizontal asymptote, and we also have to find our intercepts, right? Because we have x-intercepts and y-intercepts, right? So maybe we can look at our x-intercepts. So for x-intercept, the reason why it's actually none for this particular function is because when you plug 0 right here, so say for example your y, when this is 0, and then you have equal to negative 2 over x minus 1. When you cross multiply 0 times x minus 1, you're going to get 0, right? 0 is equal to negative 2. Therefore, you don't really have any x-intercepts, right? So this is very similar to when you're saying your x-intercept is none versus x-intercept is equal to 0. So you have to be careful with these terminologies. However, for y-intercept, right, how do you find the y-intercept? Well, you just have to plug in x is equal to 0, right? So you have y-intercept, and then this is going to be negative 2 over 0 minus 1, right? So when you find your y-intercept, you're going to see that this is equal to 2. Does that make sense? So if you know that your y-intercept is equal to 2, when you plug in 2, you're going to have a y-intercept here. So this is 2. Vertical asymptote is that x is equal to 1. Okay. That's supposed to hit 1. Okay, you get what I mean, right? There we go. Yeah, this is 1. And then you're going to see that y is equal to 0. Let's maybe label this. So 0 is on your x-axis, right? Here. And then, yeah, that's it. So all you have to really graph is basically have something like this. So you need to pass your y-intercept, and this function is approaching 1, right, from the left side, and then basically you have something like this. Okay, so that's how you draw this function, and hopefully that was pretty straightforward. Yeah, we're gonna do a lot of situations for, or I guess a lot of concepts relating to rational functions, because I know a lot of students just struggle with graphing in general, so that's why I'm starting graphing for advanced functions, and then we'll move on to applications. Okay, so interestingly, there's another rational function here. So we have in the form ax minus b over cx plus d, right? So remember what I said about the horizontal asymptotes? So horizontal asymptotes, right now, you have the same degree, right? So first of all, how do you know it's the same degree? Well, if you look at 5x minus 3, right, and 2x plus 1, the degree of your numerator would be 1, right? Because if you're looking at your x, the highest power is 1, right? And then if you're looking at your denominator, the highest power is 1 as well, right? Because it's x to the power of 1. Does that make sense? So in this case, what you need to do is divide both your numerator and your denominator with the highest power of x, which is x, right? So it really varies. For example, if you have x squared, then you would have to divide that with x squared. So highest power of x, make sure to divide that. So what is happening here is you're going to have 5, right? So 5x over x would give you just 5, right? Does that make sense? I think I just have to write that down. Okay. So you're going to get 5, and this is now going to be minus 3 over x, right? Over your denominator. So in this case, this would be 2x over x, and this is plus 1 over x, right? So you know that this is 5 and this is 2. Okay, so when you look at 3 over x and 1 over x, you're going to notice that if you're plugging in, or if you're looking at the end behavior, if you have x being, let's say, any number, right? And then if you plug in, let's say 3 over, this is just me throwing out numbers right there. So if you plug in 3 over 1000, you're going to see that this is approaching 0, right? Because 3 over 1000 is 3 times 10 to the negative 3, which is 0.003, right? Yeah. So as you can see, it's approaching 0, right? So if you plug in x, if it's not 1000, maybe you can plug in 10,000 or 5,000, right? You're going to see that it becomes 0.003, right? Which are all approaching 0. And in addition, right, or similarly for 1 over x, you're going to see that it's also approaching 0, right? So we can say that if you're looking at the end behavior, these two are approaching 0. So that's why when you have the degree of your numerator similar to the degree of your denominator, your function, right, would have a horizontal asymptote